Testing 1, 2, 3. Test 1, 2. Test 1, 2. Test 1, 2. Test 1, 2. Test 1, 2.
There it is. It on?
Okay. All right, testing? Cool. All right, so let's just go ahead and get this started a few seconds early. So I'm Lieutenant Karen Ozuski. I'm a graduate student at the Air Force Institute of Technology, so right here at Wright-Patterson, right up the hill here at Area B. And I specialize in solar physics, so all the physics going on with the sun. And I thought, what better time to discuss the sun than with the upcoming eclipse here on Monday. If there's anyone here from outside of Ohio, outside of Dayton, welcome. For all of us who are here in Dayton, this is truly a once-in-a-lifetime experience to see a solar eclipse. So we're very fortunate to have it here in our own backyards. There's not going to be another one in the continental United States for about another 20 years. So we are very fortunate to be able to be right here. So without further ado, let's get started. So what are we going to talk about? I'm going to give a brief intro into some basic solar physics and the dynamics of what's going on inside the sun. Then I'm going to discuss some different types of solar activity after we have that solar physics background. We're going to discuss how that type of solar activity impacts Earth, because I promise you it does impact everyone here in this room as well as the entire planet. Then I'm going to give a few examples on how we study this different types of solar activity. And I'm going to give my big takeaways for those of you in the room who might be considering a career in STEM, know someone who's considering a career in STEM, or if any of you are astronomy hobbyists, why you should focus on the sun for some of the work you're doing. So to get this started, I want to talk about first one of the most important drivers as to why the sun behaves the way it does. It's a concept called differential rotation. And in essence, it happens fundamentally because the sun rotates just like Earth does on its axis, but the sun is a ball of plasma. So the plasma travels at different speeds depending on which latitude it is at on the sun. So the plasma travels fastest at the equator and slower as you go higher in latitude. And what that does is it messes with the sun's magnetic field. In its most simple form, the sun's magnetic field is like a bar magnet where you have magnetic field coming into the sun and then coming out of the sun up top. But because the sun's a ball of plasma and with the rotation of the sun, the plasma is not traveling at the same speeds at all latitudes of the sun, so that causes the magnetic field lines to get drugged throughout the solar plasma. And over time, as these magnetic field lines are getting drugged throughout the solar plasma, they get twisted, they get coiled, they get knotted, they get really stressed. So this stress on the magnetic field is the heart of solar activity. This is the main driver as to why we have all of these different types of solar activity that impact us here on Earth. It is fundamentally because the sun's rotation causes this magnetic field to get very stressed. So really foot stomp differential rotation, it's really the main reason why we have to worry about the sun. So how can we really see differential rotation? Differential rotation is really manifested in sunspots, which are these blemishes that we see here on the sun. And these are basically the magnetic field bubbles that bubbled up from the interior of the sun up through the solar surface that we can visibly see, and that was due to the differential rotation. So these are those knots of magnetic field that form due to the differential rotation. And I like to call sunspots the footprints of differential rotation because they really are the way we can visibly see what's going on with differential rotation and how that magnetic field is knotting. And the reason why they appear darker is because these magnetic field bubbles are blocking the convection of hot gases underneath the magnetic field. So when those hot gases can't make it up to the surface, this plasma here is a lot cooler than its surrounding plasma, causing this plasma where the magnetic field bubbles are to be a lot cooler than its surroundings. So that's why it looks darker. So the reason why we care about sunspots is because sunspots are our indicator for where we are in the solar cycle. I'm going to get into what the solar cycle is on the next slide, but we have two periods of a solar cycle. We have solar minimum and solar maximum, and they sound exactly what they are, where solar minimum, we have a minimum amount of sunspots. On this image of the sun, we had no sunspots, and that shows that we really have that straight up and down bar magnet configuration with the sun's magnetic field. Whereas solar maximum, we have for that time period a maximum amount of sunspots that we see during that time. So that's why we care about sunspots, because they are our indicators for where we are in the solar cycle and indicate if we are at a maximum of a solar cycle or a minimum at a solar cycle. So now, what in the world is a solar cycle? The solar cycle is an 11-year period where the sun's magnetic field polarities actually flip. So if they're going in and out of the sun like this, after 11 years, it's going to be poking the other way. The physics behind that is fairly complicated. But, and to be quite frank, there is some unclear mechanisms behind it as well. But what we believe happens is that after differential rotation really takes hold and a lot of time passes and that magnetic field gets really knotted, eventually it weakens. And the sun wants to replace that magnetic field with more magnetic field, so it replaces with field of the opposite polarity. So that's why we then have this flip of the magnetic field. And this image on the right really shows that, where in 1996, you could see there are barely any sunspots on the sun. Then we move forward a few years, we're getting more and more and more sunspots until we hit 2001, and this was solar maximum for this period where there's the maximum amount of sunspots on the sun. And then we go forward a few more years, and you can see the sunspots are starting to decay from the sun until 2006, when we're back at solar minimum. So back to that bar magnet configuration. And that's the end of that solar cycle, that 11-year period. The reason why we care about the solar cycle is because typically solar activity trends with the solar cycle. And that does intuitively make some sense, because at solar minimum, we really don't have that much stress magnetic field. So if there's not much stress magnetic field, there's not a lot of solar activity. Versus solar maximum, there's a lot of stress magnetic field. There's a lot of energy stored in that magnetic field. So once it gets that stress, that's when we have a lot of energy outbursts. That's when we have those more frequent and typically higher intense, a bigger intensity of solar activity. So that's why we care about the solar cycle fundamentally, is because it really is an indicator of the amount of strength of solar activity that we're going to have. So to show this a little bit better, I have a plot here showing you the sunspot number on the solar disk versus time. And this goes back all the way to 1900, when we first started to study sunspots on the sun. And you can see the valleys are solar minimum, when there's a minimum amount of sunspots on the solar disk. And then the peaks are solar maximum, when we had a maximum amount of sunspots on the solar disk. And again, we measure the solar cycle by the sunspot number. So solar maximum, maximum amount of sunspots on the disk. And the reason why I like this plot so much is it really shows you that solar cycles are very unique, and every solar cycle is not the same. Where we could see solar cycle 19 peaked at about 200 sunspots, so a lot of sunspots on the solar disk. But our last solar cycle 24, had about 70 sunspots as its maximum. So they really are snowflakes. They're really not one and the same. There's a lot of work being done in the scientist community to predict just how fast a solar cycle will reach solar maximum, how big that solar maximum will be, and how quickly we will drop off to solar minimum. So really cool things coming there, because that could really give us some good insight on if we can predict just how big a solar cycle will get, just how many sunspots we'll have at solar maximum, then we can really get some good insight into the type of solar activity we'll have, how intense it will be, how frequent it will be, and we could do that all years in advance, since these solar cycles are 11 years long. Okay, so kind of already alluded to this, but why do we care about all the craziness of the magnetic field going on inside the sun? It is fundamentally because stress magnetic field equals more solar activity and potentially more intense solar activity. So foot stomp on that, but this type of solar activity could have moderate to very catastrophic impacts on Earth, especially as we are growing much more technologically dependent and a lot more dependent on our power grids in our everyday way of life. We need to be able to protect our technological way of life from all these solar events. So to get started on, like I keep mentioning solar activity, so what solar activity am I talking about? Start off with some definitions. I'm going to start with a coronal mass ejection, which is exactly what it sounds like. It's a giant ejection of mass from the sun, like you see here in this GIF that I provided. And they can eject billions of tons of plasma into interplanetary space. And at face of Earth, these CMEs can arrive within several hours or several days, depending on how fast these plasma bubbles are traveling. And they contain energetic protons and electrons. And specifically, they can harm spacecraft and even astronauts. As we are in an age of where we're trying to increase our space travel, increase human space travel, this is actually something that scientists and engineers within human space travel have been focusing on a lot. Because astronauts in space don't have the protection of Earth's atmosphere like we have here on the ground. So as we want to break new frontiers and colonize the moon, go to Mars, and have long-term interplanetary travel, because it does take months or even a year to travel to Mars, we want to be able to protect our astronauts from all the radiation that these coronal mass ejections fling off from the sun. Because there is an annual allowance of radiation that we can receive each year. And for people like pilots, they monitor how much radiation they receive. Since they are higher up in altitude, they do receive more solar radiation than we do. Or it's the same reason why if you get an X-ray, why your doctor will run out of the room when you're getting an X-ray. We can receive some of those radiations throughout the year, but we can't receive too much before it has some harmful effects. And for astronauts in interplanetary space, where they have no protection other than their spacecraft and their spacesuit, it's very important to make sure that they're safe through these longer-term travels other than traveling to the moon and back. But for us here on the ground, a little bit closer to home, what these CMEs can do is these highly charged particles can cause geomagnetic-induced currents. I don't know why that's always a tongue twister for me, but it is. And basically, these induced currents can be so large that they can really even physically destroy our power grids. I'm going to get into an example of that later of an event that actually did it, two events that actually happened but destroyed some technological infrastructure. But depending on how large these coronal mass ejection events are, it can disrupt our power grids, have some power loss, or even permanently destroy these power grids. And if it happens on such a large scale and we are not prepared and have the proper mechanisms in place to stop these large currents from destroying our power grids, then we can be in a whole lot of trouble and really lose power for long periods of time. So, but there is one really cool thing CMEs do provide us, which is the northern lights. CMEs, because they are really intense bursts of all these electrons and protons, do provide some of the most spectacular northern lights events. I was fortunate enough to be able to go to this exact spot in Iceland several years ago. This is not my picture, but it really is a fantastic event. If you're here to see the solar eclipse and came out of town for it, if you're here in town and you have a second bucket list item that you want to achieve, I highly recommend the northern lights. But CMEs really cause some spectacular northern lights events. So I thought this would be a great time to talk about how the northern lights happen, because everyone knows about the northern lights, but not really how they occur. So if you want a cool bar trivia fact or something, I think this could be a good one. So northern lights happen when these streams of all these energetic particles enter Earth's atmosphere through traveling down its magnetic field lines in the pole regions of Earth. And when these energetic protons and electrons hit Earth's atmosphere, they collide with a bunch of molecules that we have in our atmosphere. Specifically, they collide with oxygen and nitrogen. And if anyone here has taken any chemistry courses or quantum mechanics courses, we know that when these energetic particles collide with these oxygen and nitrogen molecules, that's going to cause oxygen and nitrogen to get into a higher energy state. And just like how when you eat a bunch of sugar and then you eventually crash in a few hours, the molecules do the same thing. Oxygen and nitrogen will want to shed off all that energy. And they do so, they shed that energy in forms of light, invisible light. And they shed that energy in the greens and the purples and the blues that we see as the northern lights. So that's how the northern lights happen. Thought it'd be cool to mention that, since not a lot of people know how they happen. But they do happen because the coronal mass ejection collides with Earth. So there could be some consequences to that, but we do get a beautiful side effect to it. Okay, so now moving on to coronal mass ejection's evil twin, which is solar flares. Solar flares are large eruptions of electromagnetic radiation. So they radiate a lot of light. And this comes from all the energy that is twisted in that magnetic field that was all twisted from that differential rotation that we talked about. And this is very similar, the process of a solar flare is very similar to how, like, if you stretch a rubber band too far and it snaps on you, that's kind of what happens with the magnetic field, where it is so stressed that, and eventually you have magnetic field lines that are going opposite directions. And once they are in a decently close proximity to one another, they can cancel each other out. And that causes a lot of energy release. And it causes a lot of energy release, which is emitted strongly in the X-ray and UV and radio wavelengths. I also want to take this time to discuss how solar flares, or strong solar flares, I should say, are often associated with coronal mass ejections, but not always. And this furthermore gets to my point that they are two very separate events. In the media, they are commonly switched out for one another because they're commonly misinterpreted as solar flares and CMEs are the same event, versus solar flares are just referring to the burst of electromagnetic radiation, whereas coronal mass ejection is talking about physically the mass that leaves the sun, that plasma bubble that leaves the sun. So now you know, the good thing is that there is a lot of media attention for these events, but if you're ever reading up on it, then now you know the difference, because they are commonly switched out from one another, since for stronger events they do a lot of the time occur simultaneously. So since solar flares emit strongly in the X-ray and ultraviolet, this can cause what are called radio blackouts. And this is because solar flares, these X-ray and ultraviolet wavelength radiations, when they hit Earth, it causes a lot of chemical reactions in the atmosphere. These chemical reactions then cause a lot of heating in our atmosphere. And this type of heating does not allow our radio transmissions to make it through our atmosphere, or either highly distorts that type of transmission. So you can send one thing up to a satellite and it can never make it because the atmosphere absorbs it, or you'll get a bunch of gibberish back. So that's why solar flares are very important to study, and more so because unlike CMEs, where they could take hours or days to reach Earth, since solar flares emit at the light wavelengths and travel at the speed of light, so 3 × 10⁸ meters per second, they can really start impacting Earth within 8 to 10 minutes of when they go off. So that's why we really care about being able to better understand and potentially even forecast solar flares. I'm going to discuss that more later on in this talk. But that's why solar flares are so important, because they really can impact Earth very, very quickly. So to give an example tying together solar flares and CMEs, I want to talk about active region 12192, which is my favorite active region. And what an active region is basically a collection of sunspots. So here we have an image of a magnetogram where it shows basically the sun's magnetic field, where you have the white magnetic field, this magnetic field coming out of the sun, and the black areas are the magnetic field going back into the sun. The reason why this active region is so peculiar, as you can see this magnetogram on the right-hand side, it's being compared to the size of Jupiter. So it is pretty large. Very, very uncommon for something on the sun. It was the biggest active region of all of solar cycle 24. Me and a few colleagues, we call it the behemoth, and it seems to be getting some traction in the field to call it the behemoth and not just 12192. But the reason why scientifically this active region was so strange is because, as you might expect, it has so much stressed magnetic field, and with stressed magnetic field comes a lot of solar activity. So it was very flare productive, and not just flare productive, had many strong flares. And as I said before, strong flares are commonly associated with coronal mass ejections. But this active region was weird in the sense that it had 1 or 2 coronal mass ejections associated with its dozens of strong flares. So a very small percentage of its flares actually had a mass ejection associated with it. There's been a lot of papers written on this active region because it is so peculiar. Everything about it, it does the opposite of what you think. So I really like this active region because it shows a great example on how solar flares and coronal mass ejections are different. They behave independently, but they can be together. But they are definitely 2 very separate events. So yeah, it's a pretty cool active region. So, I've talked a lot about different types of solar activity, and maybe you're thinking like, well, I don't remember or know about there ever being any impact to solar activity here on Earth. There was the largest recorded solar flare we've ever had happened all the way back in 1859, so almost 200 years ago. It's referred to as the Carrington event, and named after the scientist who was studying it in his solar observatory. And I have some newspaper clippings here from the time that discuss all of the bright northern light activity. Northern lights were seen all the way down the country. I couldn't find any reports of this in the newspapers, but there are reports of northern lights being seen as far south as Hawaii. So there was a very powerful storm. The biggest thing that happened during the storm, though, was the telegraph wires through all of the country actually caught on fire and were rendered useless for very long periods of time. Caused a good amount of damage. Another fun fact about this, actually, now that I remember, is there were a bunch of miners who went to bed and then were woken up, and it was so bright that they thought it was daylight. So they all got ready and went to work, and then realized that it was actually 3 a.m. in the morning, and that it was just the northern lights that were that bright. It was not the sun. It was not morning. So the biggest thing that happened with this event was that the telegraph wires caught on fire and halted communication. But at this time, that still wasn't an everyday use technology of the time. So you can only imagine if this happened in today's era, that things could be very catastrophic if we don't properly implement different strategies and standards and protocol for all of our power usage, our technological usage. And to talk about an event that happened more recent, I'm going to talk about an event that happened in 1989 on March 13th. It is commonly referred to as the day the sun brought darkness. So, start with the timeline. On March 6th, there was a large solar flare. It's categorized as an X15 flare. That is one of the ways, the X-ray flux, that we categorize how strong solar flares are. And one thing I want you to keep in mind through this slide, too, is this solar flare is actually believed to be half of the size of the Carrington event. So when we talk about the damage this flare did, the Carrington event was double the size. So keep that in mind. This solar flare also had an associated CME that was directed at Earth. So coronal mass ejection that was coming towards Earth as well. All right, then on March 13th, that's when we started getting geomagnetic storms. So that's when we had disturbances in Earth's magnetic field. That's when the coronal mass ejection then hit Earth. Another thing to note, you can see March 6th through March 13th, that's a whole week that went by until that coronal mass ejection hit Earth. So keep that in mind when we're talking about how we're preparing for these solar events, because that's a whole week. So some of the repercussions from this event were that satellites were uncontrollable for hours because there was so many radio blackouts over Earth's entire globe that we could not communicate with our satellites. So we couldn't control them, we couldn't talk to them, so we also couldn't get any data from them for quite a long period of time. I know one of the biggest impacts to that for every day is that the GOES weather satellite, which is one of the main terrestrial weather satellites we use that's up in space, measuring a lot of different stuff about our atmosphere so we can forecast weather. It eventually came back to life, but it was down for quite a period of time while this storm was going on. Another interesting thing that happened is we actually had a space shuttle in orbit at this time, and they lost sensors to their fuel systems, so they could not monitor their fuel as they were orbiting around Earth. Luckily, the sensors came back on after the storm passed after many hours, but you can only imagine how catastrophic that could be if you can't monitor your fuel, and you won't know if you have enough fuel to get back down to Earth. So luckily, that crew made it back safely, but that's just one of the things that happened, and we're very fortunate that their sensors came back on. The biggest thing that happened during this storm that made the most headlines was the power outage of Hydro-Quebec. And this caused a very long power outage for most of Quebec. And it was because Quebec didn't have proper systems in place to protect their power grids against a solar storm. Luckily, the United States did turn on, if you will, all of their systems and protocols to be able to fend off from these solar storms, which is good. So we didn't have really any power loss or any issues here in the United States. But in Quebec, they had several issues, and this was really the turning point for how we handle solar storms in today's modern era. It prompted the Federal Energy Regulatory Commission to create a bunch of standards and protocol for our whole power grid and all of our technological systems and all these procedures in the event of a large solar storm coming to Earth, so that we don't lose power, we don't lose our power grids, because if our power grids fry like they did during the Carrington event, and there's a large amount of power grids that caught on fire and got decimated, then that takes a long time to rebuild. And even if it's a worldwide event where the whole world isn't prepared, if we lose everything, then our whole lives are really we're gonna have to restart from scratch. And there's so many things we don't even think about anymore. Like, we wouldn't be able to travel. There's no GPS usage, no telephone usage. Even things with food, we can't import and export food. There'd be a large food shortage. And those are just a few examples I can think of off the top of my mind right now. But this was really, 1989 was a huge turning point for handling solar events in the era of technological dependence. Okay, so now that I've scared everybody about the sun, let's talk about how we're studying it so that we don't have these issues. And this first study I want to talk to you about is something that I was a part of, and we always joke about that we're doing it so that we can prevent anyone from having issues watching the Super Bowl. This is something that we want to model the atmosphere so that everyone can watch the Super Bowl. There's no blackouts in the atmosphere from being able to communicate with our GPSs or our satellites, and everyone has the ability to watch live television when it's most important. So to start off this conversation, I'm going to start with the spectrum of light. So you can see right here we have our visible light. That's the light we see. But the range that we're mainly concerned about is the X-ray and the UV rays. And this is very similar along the lines of when I talked about solar flares, why we're concerned about those. It's because that type of radiation, when it interacts with the atmosphere, can cause a lot of issues with our satellites. So ultraviolet radiation comes in mainly two forms. One being from solar flares, what we talked about, and those solar flares emit a lot of ultraviolet radiation. The second thing is that there's a lot of heating that goes on within the solar atmosphere. And all those reactions cause a lot of UV radiation to come and get incident upon Earth and interact with our atmosphere and cause a lot of heating after some chemical reactions. And these two forms of UV radiation in our atmosphere cause two main problems. Radio communication, which we've talked about a lot, atmosphere heats up. The radio wavelengths that we try to emit through the atmosphere get absorbed, and we either can't communicate with our satellites or our communications are highly distorted. So that's where the Super Bowl comes into play. But then there's also satellite orbit drag. So if you think about it, when the atmosphere is heated this much, it becomes a lot denser. And when a satellite is traveling through a thicker fluid, then its orbits are going to be changed. So in order to prevent satellites from crashing into one another, which shockingly does, there's a lot of junk up there in the atmosphere, it can happen, or either satellites from crashing into Earth's atmosphere and burning up, we want to be able to properly model our atmosphere when we have all this heating due to the UV radiation coming from the sun, so that we can properly monitor our satellites, make sure they're safe, make sure they're orbiting correctly, make sure they're not crashing into anything. Okay, so I know what everyone must be thinking, which is why can't we just measure the UV radiation? Why do we have to model it? Why do we have to let the computer create some equation for everything going on? Why can't we just send up a sensor or put up a sensor to be able to just measure it? There's two main reasons for that. So what this plot shows, it's a great plot. It shows what percentage of light is absorbed by Earth's atmosphere. All the way over here is all the UV radiation on this whole left-hand side of the plot. And you can see that its absorption in Earth's atmosphere is almost at 100%. meaning that most of this radiation is absorbed by Earth. So we can't measure it here on the ground. And that makes it very time-consuming and expensive to send something up into space to measure this type of radiation. So it is very difficult to measure the UV radiation because we can't very well easily measure it, and we have to send stuff into space to do it. Off topic, but I think it's worth noting because I had a professor at my undergraduate university discuss this with me, and I think it's very interesting. But you can see this rainbow light right here. That's our visible light spectrum. That's the light that we can see. You can also notice that it is barely absorbed by Earth's atmosphere, meaning like all the visible light that the sun emits makes it through our atmosphere here onto the ground. And that is most likely why that humans and all these animals have adapted to be able to see the light that we see. Because if you can imagine, if we saw light in the ultraviolet wavelengths, it'd be a pretty dark world. We wouldn't see anything. So that's why the human body and all these animals here on Earth, too, have adapted to see light in the visible spectrum rather than anything else because it makes its way through Earth's atmosphere. So cool side note, but I thought that was worth mentioning. All right, so reason number one why we can't just measure the UV is it gets absorbed by Earth's atmosphere, and it's very expensive to send stuff into space. Reason number two is even when we can send stuff into space, it is constantly susceptible to instrument degradation and aging, and that's because this instrument is pointed at the sun 24/7. And when we talked about all of like the coronal mass ejections that go off, and the sun is constantly just emitting a steady stream of particles called the solar wind. That causes a lot of degradation on all of our instruments because these energetic particles strip away the electrons from our instruments. So over time, as these instruments are just staring at the sun, they can degrade over time. Their measurements become less accurate, and there's non-negligible errors that we get in measuring these quantities. So the best thing that we have right now is the thermosphere, ionosphere, mesosphere, energetics, and dynamics mission. Most people call it timed. And on board that is the Solar EUV Experiment C. So most people call it Time C. And this is a state-of-art instrument that we have, but one day it is going to start aging and degrading faster than when we can keep up. So there's therefore significant importance in modeling how our atmosphere responds to all this radiation rather than just solely relying on the measurements themselves, because it is so expensive and time-consuming. The amount of time it takes to propose and send up an instrument into space takes years, if not decades. It takes a lot of time. If any of you are familiar with James Webb, not trying to age myself, but that was a proposed telescope that NASA proposed before I was born. So it shows you just how long it really takes to get up there. So we really want to model this stuff so we can better understand it. And at the end of the day, I know I'm tuning in for all the exciting March Madness games tonight. I like to know that our atmosphere is not blocking any of those signals from getting to me, so I can watch all of those television and all of the games live and the Super Bowl live. So when we're able to watch all of our March Madness and Super Bowl games and anything else you could be watching live, just thank your solar physicists for that we can do it. Okay, so topic number two I want to talk on, which I alluded to earlier, is solar flare forecasting, which is very similar to how we forecast weather here on Earth. And there's a huge push right now in the solar community in order to do this, because solar flares can wreak so much havoc on our technology and our radio communications. And they can do so quickly because they emit in light. So this radiation can hit Earth within 8 to 10 minutes, can hit very fast. So there's a huge push to be able to predict not only where on the solar disk they will happen, but also when they will happen. That's the big push right now, to know when these solar events will impact Earth. But there are still so many unclear mechanisms to how solar flare onset even occurs. So, and this is really due to we can't really reliably measure the magnetic field in the solar atmosphere very well yet. More so, it's in the sun's corona, which we'll actually be able to see with our very own eyes with the eclipse. When you see the eclipse, you can actually see the sun's atmosphere. So otherwise, it's very difficult to see. So there is still some ambiguity onto how solar flare onset really occurs, because we can't directly measure that magnetic field. So solar flare forecasting is really still in its infancy. but it's still very important. There's many scientists all over the world and the country who are dedicating their entire careers towards trying to solve this problem. I hope to be one of those people that can at least help fit a puzzle piece into that problem. So there's still so much more to come on this. Really intriguing science. It's a very new science. Yeah, stay tuned, because I'm sure there's going to be some really cool things in the media once this stuff gets solved. So similar to that route, I want to talk about this one because I do think it's the most dazzling event that happens on the sun, but it is also my field of expertise, which is coronal rain. And yes, it does rain on the sun, not like it does here, but it does in fact rain. And what coronal rain is it's we have these magnetic field lines poking out from the sun from that differential rotation. And when the plasma at the solar surface gets heated, it causes this plasma to get more dense and fill up these magnetic field lines that are protruding into the solar atmosphere. And then this plasma in the magnetic field lines then cool non-uniformly, which then causes these plasma rain droplets to drain from these magnetic field lines and fall back to the solar surface like these plasma rain droplets. I say droplets, but you could see the scale size to Earth right here. These plasma droplets are about the size of Earth, if not bigger. They're definitely bigger than Ohio, I can say that. So it's a very beautiful event that happens. And the really cool thing about the plasma filling up these magnetic field lines is that that's really the main visible way we can actually observe the magnetic field in the solar atmosphere. If you remember when I talked about solar flare forecasting on the last slide, that's one of the reasons why we are not have not made strong headway in the forecasting part of predicting solar flares and being able to forecast the timestamp on when we'd expect a solar flare to go off, because we can't reliably see these magnetic field lines on the sun. But the plasma filling up these magnetic field line loops really helps for us to visually see and observe what's going on with the magnetic field. So there are two forms of coronal rain. The first form is thermal non-equilibrium rain, which is, so we all just call it T&E, but it's the rain that occurs really all day on the sun. It's normally smaller rain showers, a little mist of rain, and it just happens due to a non-uniform heating of plasma going on all the time on the sun, because it's not heated the same way throughout the whole solar globe. Whereas there's another form of rain called post-flare rain, and that's what this video is showing here, which is the brightest and most intense rain storms that we get. It's a solar hurricane, if you will. And it happens because when a solar flare goes off and it releases all that energy, it really heats up that plasma right underneath it. So when that plasma is very quickly heated, it gets flung up these magnetic field lines, and the brightness shows you just how hot this plasma is, and then it eventually cools. So that's the type of rain I also will be studying a lot too, is that rain following flares. There's a study that was released about 2 years ago that showed that the duration of rain events that we get is highly dependent on the strength of the flare. So a smaller flare will yield shorter rainstorms, versus a strong flare typically yields some bigger, longer storms, if you will. So one thing that I'm looking at right now is, can coronal rain be an indicator for solar flare forecasting? There seems to be a trigger where right before a solar flare, the plasma from these magnetic field lines just drains. At least that's what I've observationally seen. And I'm looking at to see if when that plasma drains from the magnetic field lines, how quickly it drains or when it drains, does that give an indicator of solar flare strength? Can give an indicator of when a solar flare is going to go off, and looking at all the different magnetic field properties associated with that to see if we can actually identify a proper trigger on what can be a trigger for solar flare forecasting without needing to look at this atmospheric magnetic field. So more to come on that, hoping to have some results on that within the next few months, hopefully by the end of the year, but hopefully that will yield something useful, and if it doesn't, then, well, rain is pretty to look at, so I'm not losing. Okay, so on our way to wrapping up this talk, if I haven't convinced you yet just how awesome the sun is, because I personally think it's pretty amazing, but this is geared towards more our early career people in the room, anyone who's considering a career in STEM, or if you know someone who's considering a career in STEM in science, engineering, or math, or for any of our astronomy hobbyists in the room and you want to find a way to focus on any of the work you're doing, I want to give my top 5 reasons on why you should focus on the sun. So the sun is beautiful and you get to stare at it all day. So through a computer, of course, don't go looking out with your eyes without the proper eyewear, but these are all real images. All the images I've shown all day are real. They're taken mostly from the Solar Dynamics Observatory. It's a space-based telescope that is it's in space and it's staring at the sun 24/7 in many different wavelengths of light. And I'm an astrophysics degree by background, and when I wanted to focus what I was doing, this is why I wanted to study the sun, because you get to stare at these high definition images and movies all day. And it really is a beautiful thing to be able to do for a job. Okay, so reason number 2, there are so many meaningful applications to really have a worthwhile career in solar sciences. Especially for people interested in astronomy and astrophysics. It's one of the few careers in that field where you're actually going to be doing something that has a direct impact to everybody here on Earth. We spent our whole talk talking about the different types of solar activity and how they impact us here at Earth. And solar physics and solar sciences is really one of the only fields in astronomy where you get to directly do something that has a large impact to everyone here on Earth. All right, so this was an important point for me. So all the space nerds out there who also like to go to bed early like I do, there are no late nights required with studying the sun. With all other fields of with astronomy and astrophysics, you still have to stay up late at night to use their observatory because it has to be dark out to observe whatever you're looking at. Versus the sun, if you're going to observe it in an observatory, it has to be during the day. So you get to go to bed at a good hour. Definitely one of the reasons why I wanted to join this career field. Similar on that, so science commonly requires you to propose and bid for time using some type of equipment, an instrument, a lab, or observatory, or space-based telescope. That requires a lot of writing to be able to use that instrument, requires a lot of time waiting, and then a lot of time that you have to spend when you have to point that telescope or instrument at what you want to study. Great thing about solar science is most solar data is open source, meaning if you wanted to right now, I can show anyone if they want to how to download solar data right now. All of our solar instruments are just faced at the sun 24/7, so you don't have to propose to move a telescope anywhere because you just want to study the sun, so it's not going to move anywhere. And I'm sure that if we have any younger folks in the room, that might not be a point that's all that important right now, but I assure you in graduate school or when you're working, being able to just sit down and do research all the time versus spending most of your time proposing or like fighting for time to use some type of instrument that you really want to use, it saves a lot of time and a lot of headaches. So that is a great reason to study the sun, is all the data is available at your fingertips whenever you want it. All right, and finally, the most important point, and it's in bold because of that, there's so much more that we don't know about the sun than we do know. And I alluded to that several times throughout this talk, where there's still some very unclear mechanisms as to why some things occur on the sun. And because there's so much more that we don't know than we do know, there's so much left to discover, and that's something you can be a part of. We are constantly having new instruments like this. SDO is about a decade years old now, and is unveiling new science every single day. And it's not just science that no one really, I don't want to say no one cares about, but it's national headline science that's coming from the sun these days. And because there's so many major things that are left to discover. So if you really want to make a key contribution to science, solar physics and solar sciences are really a great way to do that, because there's so much available to discover. And even if you're not doing science as your career field or anything like that, there's programs called the Citizen Science Program where you can just get on your computer and help scientists solve their data sets. It's on zooniverse.com. And there's been some very intriguing results found from that where people all over the country are logging onto their computers to help contribute to all this science. So feel free, if you want to talk about that more afterwards, I'm more than happy to talk about that and answer any questions you have. But there is so much left that we don't know about the sun and so many ways to get involved that I can't speak highly about this career field enough or this research in this science enough. All right, so almost done. So my final takeaways, the sun is awesome. I hope I don't need to belabor that point anymore because I think it's pretty awesome. And I hope I convinced you of that too so that we all can leave here today with a big appreciation for the sun when we're looking at the eclipse on Monday. But staring at this beautiful ball of plasma all day is pretty great. But it can easily change our lives within minutes, and that's something we need to be prepared for. It's great that that event in 1989 really prepared us to protect our technological infrastructure, our power infrastructure, so that we can be ready for that next big solar storm, that next Carrington event, because it will happen one day if we like it or not. So we need to remember that the sun can also change our lives in minutes and be ready for that storm and be ready to protect our technological way of life from it. There are so many opportunities to join solar science. Again, I'm more than happy to continue talking with that with anyone, but yeah, it's really an amazing career field, and I hope those 5 key points really helped anyone here, or if they could help anyone that you know who's not here. And finally, I'd be remiss if I didn't say to observe the sun safely on Monday. Wear your glasses when you're supposed to, when you're staring up the sun. You can take them off during totality, but when that moon starts to move off from the sun, put them back on. And I want to stare at the sun all the time too, but protect your eyesight. Don't be like Galileo where he lost his eyesight staring at the sun. And wear your solar eclipse glasses when you should. But without further ado, enjoy Monday. It's really a once-in-a-lifetime experience. I think it's hard to be more excited than I am about it, but I hope you're just as excited for it. And yeah, thank you so much for coming out, and I hope I helped give everyone a little bit of appreciation about the sun. Thank you.